let's see, last time we actually did an example, an application of Zorn's lemma, right, where we showed that every vector space has a basis. And now what I want to do is one more example using Zorn's lemma to prove something, and this time it's going to be involving ring theory. So just a little quick preliminary here. So let's let R be a ring. Remember, when we say a ring in this class, we mean commutative with 1. So let me just remind you, so let's say recall a proper ideal, let's say capital M in R is maximal, right, if it is not properly contained in a proper ideal of capital R. And so let's say, in other words, or that is M is maximal if I equals M or I equals R whenever I is an ideal. Such that it lives in between M and R, right? So what this says then, maximal, M is maximal if anytime you have this situation, either I equals M or I equals R. Okay, so I'm just reminding you that's the definition of maximal ideal. And so now I want to state and prove a theorem. I guess I can put it here. Involving maximal ideal. So the theorem, so let's let R be a ring, and let's say I want it to be a proper ideal. So I be an ideal. Then there exists a maximal ideal. Let's call it capital M sub I, such that I should say of R, maximal ideal of R, such that I is contained in M sub I. So what is this saying? In a ring, every proper ideal is contained in a maximal ideal, right? So as long as, if you're an ideal that's not equal to the entire ring, then you have to be contained in some maximal ideal. And so the proof is going to be very much like the every vector space has a basis proof. What we're going to do is set up a poset, show that every chain in that poset has an upper bound, then that will produce a maximal element. That maximal element will be our maximal ideal. So somehow the poset that we create should have something to do with our chosen ideal, our proper ideal, capital I. So for the proof, let's call it P sub I be the set of all proper ideals, I guess. All proper ideals of R that contain capital I. In other words, let me write this as a set. So that is P sub capital I is going to be the set of all proper ideals that contain I. And I don't need them to properly contain I. So it's going to be I contained in A want to be proper, so we'll say contained but not equal to R, where A is an ideal, right? So set of all proper ideals that contain I. Now we're going to partially order P sub I by inclusion. So we partially order P sub I by inclusion. Okay, so let's just think about what's going to happen here, right? If we can show that every chain has an upper bound, then P sub I is going to have a maximal element. So what will that be? It will be, in the appropriate sense, it'll be the biggest ideal, biggest proper ideal that contains I. Okay, so now what do we need to do? We need to find a chain, or choose an arbitrary chain in P sub I, produce an upper bound. So let's let C in P sub I be a chain. Okay, now what are we going to do? We need to create an upper bound. It's going to work exactly the same as we did before, right? We're going to take the union of our chain. So let's say and define capital U equal to the union. Let's say X element C X. So we're taking the union of all the elements in the chain. Okay, so what do I need to do? So I need to show that it's an upper bound. Okay, so we show that U is an upper bound for capital C. Now, now what? So it's clear that I is contained in capital U. Yeah, okay, so let's say it like this. So clearly, capital I is contained in U. Why is that? Well, because every single I in C is an ideal, right? It's one of these A's, right? So it's an ideal that contains I. So when you take the union, of course, it contains I. And what? Since, we'll say set and, comma, since each little x is in C, and since each x in C is proper, we know that 1 is not an element of X for each little x in capital C. Why is that? Well, as soon as you're an ideal that contains a unit, in particular if it contains 1, then it equals all of R, right? So since each one of these x's is a proper ideal, it does not contain 1, which means then that when we take the union of all of those x's, it won't contain 1 either. So it follows that 1 is not an element of U, and so U is a proper subset of, well, I guess for now we're just going to have to say proper subset of R. All right. So now, what do I need to do next? I need to show that U is an ideal, right? Because what we want to do is we want to make sure that U lives inside P sub I. So far what we have is that we can put U right here as soon as we know that U is an ideal, right, then U will be one of the elements in P sub I. So let's pick, let's say little a and little b in capital U. What does that mean? Well, U is the union of all these x's, which means that A lives in some x and then B lives in potentially some other x. So let's call them, I guess I call them I sub A and I sub B. Right, so then there exists, say I sub A and I sub B in C, such that little a is an element of I sub A and little b is an element of I sub B. Now, capital C is a chain, which means that one way or the other, one of these is contained in the other. Either I sub A is contained in I sub B, or I sub B is contained in I sub A. That's what it means to be a chain. And so I'm just going to assume that I sub A lives inside I sub B. So since C is a chain, we can assume, without loss of generality, that I sub A is contained in I sub B. In which case, both A and B live in I sub B. So, in this case, since I sub B is an ideal, we have, well, it's going to be closed under subtraction and under external multiplication. So we have A minus B is an element of I sub B, and RA is an element of I sub B for all little r in capital R. Well, okay, so if R sub A and A minus B live in I sub B, that means that they live in U. So it follows that A sub, or A minus B and R sub A are elements of capital U. And so what? U is an ideal of R. So now what we can conclude is that U is an element of P sub I, right? So we now conclude, that looks just weird. We now conclude that right, that U is an element of P sub I, since say X is contained in U for all X in C, we have that U is an upper bound for C, right? It is an element of P sub I that contains every element of the chain. All right, that's what it means to be an upper bound. So now we can apply Zorn's lemma. So by Zorn's lemma, P sub I has a maximal element and I guess I want to call that m sub, well, I guess I just called it m. I don't know why I didn't call it m sub I. Yeah, let's call it m sub I. So what does that mean then? Well, if you live in P sub I, then you're a proper ideal of R that contains I. So, so this means, or so note that M sub I is a proper ideal that contains proper ideal of R, proper ideal of capital R that contains I. So now we need to show that M sub I actually is maximal. So suppose, let's say J is an ideal of R such that M sub I is contained in J, which is contained in R. Now, if J is a proper ideal, then that would tell us that J, because I lives in said M sub I, so let me write this down. So if J is proper, then we have what do we have? We have oh yeah. So then we have I contained in J, and so J is an element of P sub I. Now, by the maximality of M sub I, that would force us to conclude that J is equal to M sub I. So by maximality, or let's say since M sub I is a maximal element, of P sub I, we conclude that J would have to equal M sub I, so J equals M sub I, and so then by definition M sub I is a maximal ideal. So therefore M sub I is a maximal ideal of capital R. So what did we do by using Zorn's lemma? We produced, well, it was a maximal element, and then we showed that maximal element in this setting means maximal ideal that contains I. Right? That completes the proof. We've shown, we chose an arbitrary ideal. We showed that there's a maximal ideal that contains capital I. So you should notice that, I mean, I said this earlier, the proof of this particular theorem, the flavor is very, very similar to the one we did when we were doing vector spaces, right? We set up a partially ordered set that does what we want it to do, right? That's sort of you do need to phrase it correctly, or, you know, set up the partially ordered set. Then you do, what do? You choose an arbitrary chain. The upper bound almost always is going to be the union, or it'll be somehow the biggest object, right, that you can form, the maximal object that you can form. It will turn out to be an upper bound. You apply Zorn's lemma, you get what you need, right? So now you can see why typically in books, right, once you've done a few proofs of Zorn's lemma, right, the authors don't actually include the proof because you'll know how to set it up, and so it is very common that you'll see something like this. Not necessarily, I mean, every once in a while they'll actually use the term Zornify for their proof, or they'll just say, you know, this is a routine application of Zorn's lemma. Okay, so that completes or concludes the preliminary stuff for this class, right? I mean, this is kind of a little bonus section at the beginning, right? I think it's important that at some point in your math careers you see Zorn's lemma, you learn about the axiom of choice, and this is the way that we did it. So now what I'm going to do is actually start the meat of the course here, and this is going to be chapter 1, fields and field extensions. And let me just check the book real quick here. So in your book, and I'm not going to do my numbering, I mean, so if you notice, I mean, chapter 2 of this book is the Zorn's lemma stuff. The chapter 3 is about rings, stuff that you would have learned in Math 482 or an equivalent course. And then, so chapter 4 is where we start field extensions. So my numbering is not going to match the book exactly. This is chapter, I'm calling it chapter 1, it's chapter 4 in the book, or it corresponds to the material from chapter 4. Okay, so we're going to talk a little bit about fields, or I'll get started on the field material here. I'm not sure how long I've been going so far. 20, oh, we got plenty of time. Oh, one thing to notice in this book, I mean, in previous classes, I use a capital F for field. In this book, for whatever reason, their default symbol for field is K, so I'm going to try to stick with the book's notation. So for a field K, the intersection of all fields, of all subfields, of K is a subfield, and it's called the prime subfield. So this is a, well, let's just say it's called the prime subfield of capital K. You can check very easily that if you have a bunch of subfields, any collection of subfields, and you take their intersection, it is a subfield. And so you can think of this as the smallest subfield of K, in the sense that it is contained in every single subfield of K. Now, so let's say recall. And if you haven't seen this, it's very easy to check. The mapping let's say phi from Z into K, given by, or let's say induced by phi of 1, the number 1, equals the multiplicative identity, is a ring homomorphism. Now, there's two choices for the characteristic of K, right? In fact, so remember, if you have an integral domain, the possible choices for characteristic, either a prime number or 0. So there's two cases to consider here. So in the case that the characteristic of K is equal to P, right, where P is prime, then what? So in that case, we have that the image of phi is isomorphic to ZP, and so what? And so the image of phi is a subfield of K. Now, ZP itself has no proper subfields, and so that tells us, right, ZP, right, there's no proper subfields of ZP, and so that tells us then that the image of phi is exactly the prime subfield of K. So, since ZP has no proper subfields, it follows that the image, image of phi is the prime subfield. So what that tells us then is if you have a field of characteristic P, then the prime subfield is isomorphic to Z sub P. Now, so there's the first case. Now we want to consider the second case, which is when we have characteristic of K equal to 0. So if characteristic of K equals 0, right, so then the image of phi is going to be isomorphic to Z, right? If the characteristic is 0, then the kernel of this mapping is going to be trivial, right? And so that tells us then that Z will be isomorphic to its image within K. Now, now what? Okay, fine. Well, I mean, what does this tell us? It tells us that K has a subring isomorphic to the integers. Fine. Now, what I want to do, well, let me just say it like this. So we will extend phi to a mapping, and I'm going to call it phi hat. So phi hat from Q to K as follows. Now, when I say extend phi to a mapping phi hat, what I mean is that it's going to be a function. So you can think of the integers as sitting inside Q, right? In fact, Q is the field of quotients, or isomorphic to the field of quotients of Z. And sorry, I just lost my train of thought for a second. So I want to extend this mapping, and what that means is that if we look at phi hat restricted to Z, then phi hat will equal. I'm sorry, I just suddenly just spaced out for a second. So what it means when I say extend is that phi hat restricted to Z is equal to phi. Sorry, that's the easy way to say it. So how are we going to do this then? So I want to define phi hat on a fraction, right? So given, say, R over S element Q, define phi hat of R over S equal to phi of R times phi of S inverse. Now, remember that the set of rational numbers is really a collection of equivalence classes. So for me to go any farther, I need to actually verify, or you should verify that this mapping actually is well defined. So I'm just going to say check. That phi hat is well defined. And so what I mean there is, if we have another fraction, right, r over s equal to r prime over s prime, then we want phi hat of r prime over s prime to be exactly the same as phi hat of r over s, right? So you can check. That's just a little arithmetic to verify. Now, also, so let's say it like this. So now also check that phi hat from Q to K is a monomorphism. So that is, it's a ring homomorphism that's 1 to 1. And so phi, nope. So image of phi hat is isomorphic to Q. Okay, so now let's just take in subfield. So let's let L be a subfield of K. So this be a subfield. If n is any integer, then phi of n is equal to, how's that go? It's going to go n dot 1. Well, 1 lives inside L, which means that n dot 1 lives inside L. So this is inside L. And so what that tells us is that the image, let's say, and so the image of phi, do I want to say phi? Oh, yeah, okay. So that means that the image of phi is contained in L. And from that, we can say, therefore, the image of phi hat is contained in L, right? If we have every element in the image contained in L, thinking about how phi hat is defined, right? It's defined in terms of phi. And because L is closed under multiplication and under inverses, we know then that the image of phi hat has to live inside L as well. So it follows, I'm starting to read my notes here. So it follows that what? Follows that the image of phi is contained in the what? Is contained. I get it. Okay. Is contained. Sorry, I guess I'm losing it now. I'm getting a little spacey. So the image of phi hat is contained in the prime subfield of capital K. Okay, so what's going on here? What we showed is that the image of phi is contained inside every single subfield of K, which means that it's contained in the intersection of all subfields of K, right? And so that, which is by definition the prime subfield, right? So we know that the image is contained in the prime subfield. So since image of phi hat, right, is isomorphic to Q, and Q has no proper subfields, we conclude that the image of phi is the prime subfield of capital K. Right? You can think of the prime subfield as the smallest one. And so, since the image of phi is isomorphic to Q and Q has no proper subfields, that means that the image of phi has no proper subfields as well. Right? Which means that it is the smallest subfield of K. Okay, so what did we just prove? Let me combine this. Let's combine this into a theorem now. So we have proved the following. And I'm going to start numbering things now that we're in our first chapter. So theorem 1.1. Let K be a field if characteristic of K equals P, then the prime subfield is isomorphic to ZP if the characteristic of K is equal to 0, then the prime subfield is isomorphic to Q. This is a theorem, if you remember back in Math 482, for those of you that just finished Math 482, I actually stated this theorem and kind of waved my hands at it a bit. And so now here's an actual proof of this fact, right? Anytime if you have a field, it is going to contain a field that's either isomorphic to ZP or isomorphic to Q, depending on the characteristic, and that is the smallest subfield sitting inside your field. Okay, I think, yeah, that's a good place to stop for today. So we will pick up for the rest of that later.